In this video, we will have a closer look at other length-oriented objects. The first object is the converter. Converters are used to model materials handling equipment. When the MU moves onto the converter, it either passes straight through in the conveying direction, or it is, for example, lifted onto a laterally moving transport level by a lifting mechanism and then conveyed laterally to the left or laterally to the right. As you can see, we have already built a finished model, which we will now rebuild. First, insert a source and a station. Then insert a conveyor, the converter, another conveyor, and a drain. We will now attach a conveyor to the converter. If we open the dialog of the converter and click on the drop-down at Default Exit, we can see 4 output directions. The directions of the converter can be shown in detail in the online help. To open the help, you must click on the Help tab and then on Help on Object. Now the help will open in your default browser. As you can see, a detailed description of the directions of the converter is given. Here you can also get additional information about the converter. The converter has 4 output directions. 0 is the default output direction, which is the straight output. 1 is the right output direction, and 3 is the left output direction. 2 is the backwards output. We will now change to the tab times. As we stated before, the converter can lift an MU onto a laterally moving transport level by a lifting mechanism. At moving time, we can set the time it takes the conveyor to lift the part and to then lower itself and move back to the default position. If we now have a look at the strategy, we see that is set to default exit and the value is by default 0. We can change this and set the default exit to 3, and the parts will now be conveyed on the attached conveyor. Let's change the exit strategy now. As shown in the previous examples, we will use a data table to specify attributes of our parts. We will use screws and nuts in this example. First, we create a new data table and drag and drop it to the source. The reason for doing this is that we want to parameterize the source. In this way, we can let the source produce parts according to the parameters we will enter in the data table. If you are not familiar with parameterizing the source, we recommend you to watch the previous videos. We will now duplicate the part in the MU library. In this way, we create a new user object. Then we rename the parts in screw and nut. To differentiate the parts visually, we will use 2 different colors. To edit the colors of the parts, we right-click Screw and then click on Edit 3D Properties. Here we click on the tab appearance. Now we check the box material active. This cuts the inheritance and we can edit the color of the part. At diffuse color, we select red. We do the same for the nuts. Now we open the data table and drag and drop our parts from the class library into the first 2 rows. We now set the number of parts to be produced to 2. Since we named the new parts already screws and nuts, we can leave the name column empty. In this way, the instance part will inherit its name from the class. We can close the table afterwards. Now we will define the exit strategies based on these names. Screws should be conveyed to exit 3 and nuts to exit 0. To do so, we change the strategy in the dialog of the converter to MU name. Now we must set the checkbox next to the field Open List. This will cut the inheritance. We need to do this to be able to create our own specification at the instance. In the first row, we will type under name screw and set the side to 0. Then we press the return key and type nut and set the side to 3. Now we are ready to run the simulation. As you can see, the screws are conveyed to default output 0 and the nuts are conveyed to output 3. This concludes the first part of the video. At the second part of the video, we will have a closer look at further length-oriented objects, namely the angular converter, the turntable, and the turn plate. We will start with the angular converter. The angular converter changes the conveying direction of the mobile objects from lengthwise to crosswise conveyance, or from crosswise to lengthwise conveyance. As you can see, we have already built a model, which we will now rebuild. First, we will insert a source, a station, and a conveyor. Then we will insert the angular converter and a drain. If we start the simulation now, you will see that the parts are smoothly conveyed. Keep in mind that only one part can be located on the angular conveyor at any given time. We can also see that the conveying direction of the part changes after it passes the edge of the converter. We could try to achieve the same model by using conveyors or converters. However, the angular converter combines two features that are not possible to achieve with converters or conveyors. First, it can have an entry speed and an exit speed that you can set separately in one dialog window as shown. Second, it has a smooth transition at the angle. If we use two conveyors that are attached to each other, the objects on the conveyor would make a jump at the angle, and you could not set the speed of each conveyor in one dialog. If we use a conveyor with an edge, the parts won't change their conveying direction. If we now open the dialog of the angular converter, we can set the entry and exit speed. We will set the entry speed to 2 meters per second and the exit speed to 0.5 meters per second. If we start the simulation again, we can see that the parts are conveyed with two different speeds. The second object we will look at is the turntable. You can use the turntable to model a rotating platform, which moves the part onto one of several connected material flow objects or turns it around. Let's have a look at an example. First, we will insert a source, a station, and a conveyor. Then we will insert a turntable and one further conveyor, which we then connect to the turntable. As you start the simulation, the turntable will wait until the part is entirely on the turntable, and then turn to the direction of the attached conveyor. Then it will convey the part on the second conveyor. Keep in mind that on the turntable can only be one part located at any time. We will now insert a second conveyor and two drains. Then we will define an exit strategy. To do so, double-click the turntable and go to the Exit tab. We change the strategy to percentage. Then we need to press Apply to show the additional parameters for the strategy. In this case, we can do a 70-30 split. Now the turntable will distribute the parts accordingly when we start the simulation. The third object we will look at is the turn plate. You can use the turn plate to model a rotating platform, which rotates the loaded part and ensures the uniform orientation of the leaving part. A typical example is in the package shipping industry, where all packages must be rotated to a uniform direction so that a scanner can automatically read the barcode holding the address information. To use the turn plate, we insert a source and a station and connect the station with a conveyor. We attach a turn plate now and connect the turn plate to another conveyor. In the dialog of the turn plate, we can adjust the angle of the rotation. By default, it is set to 90. We set the angle to 720. Now the part will be rotated 2 times. In this way, we can simulate a packaging process. Keep in mind that you can only enter multiples of 90 degrees. Now we change the angle of rotation to 180 and start the simulation again. We will now also see that the conveying direction of the part will be changed. This concludes our video about length-oriented objects.